Good morning. Today we're going to take a look at how to perform simple linear regression using Matlab. Let me share my screen and we'll get started. Okay. So um, just like any problem that we've done already, we've got to take our data, and I'm using this cooling curve data that we've used before. And I'm just going to copy it and drop it into Matlab. So get a new variable. I'm going to drop it into Matlab. Boom. Okay. I'm going to rename my unnamed matrix into data. And then I'm going to call out these two column vectors. The first column vector is time. So I'm going to say time is equal to data all rows and the first column. And then temperature is equal to data all rows second column. Okay, and I'm suppressing the output. And so what you can see here is we've got 62 records in each of these vectors. Okay, so it's column vector of length 62. It's all paired data, so that if I see this 65.0715, that corresponds to time 0. And so each of these is a one-to-one pairing of time and temperature. Okay. Now, suppose what we wanted to do was take a look at those two variables and their relationship. The very first thing I want to do is I want to make a scatter plot. And the x variable first, and then the y variable. Okay. And that'll give me a scatter plot. I had 2 probes, remember, that I put in the zombie, and those probes, the first probe is on the top, the second probe is on the bottom. If I had other probes, they would be scattered in the middle or a little bit outside, and then there would be some variation. As you can see, even with these, there's some variation in data point by data point, how much they change. So now, what I can do a lot of things. You have tools for looking in. You can do, you can do basic fitting and data statistics from here. So I can do basic fitting. Come on, there it goes. Boom, boom, boom. Come on, figure 1 basic fitting. All right, sorry. So I can do a linear fit, right? And it'll give me the line of best fit. So they're that easy to do a linear regression. Okay, very easy. If I wanted it to be cubic or other polynomials, I could also put those in there. The R squared, the coefficient of determination is about 97%. So this is a very, very good model. The root mean square error, that's the standard error of the slope, is about 0.93. So this is a very small root mean squared error, very high R squared. We're feeling really good. Okay. On the other hand, we also know that this is not truly a linear model. You can see that these points are getting closer to each other as we get closer and closer and closer to the ambient temperature in the room as the zombie cools. Okay, so this should asymptote out as a bounded exponential. And so we would have to deal with that in some way by transforming the data. But you can just do it that way. That's very easy. Okay. There's another way to do it that gives you a lot more information, and that's what's called regstats. It's a mathematics. It's a function called regstats, and so I can say, we'll say stats. Just call out a structure is equal to regstats. Then still, and this is now like in linear regression, we regress y, the dependent variable, onto x, our predictors. Okay, so we have to put y first. We have to put now temperature first, and we're regressing that on time. Okay, and we'll make it linear. So you have to specify the model that you're going to use in regstats, and it only does polynomial models. If we want to do exponential models, we will show you how to do that after the midterm. And you can see it thinks a little bit and gives me a structure called stats. Okay, gives me a structure called stats that regresses temperature onto time with a linear model. If we go in there, here's all sorts of garbage, right? But the things that you're going to be interested in are these. You're going to be interested in beta. Okay, and this is that matrix of parameters that we've estimated. The first parameter is the intercept, beta 0. The second parameter here is beta 1, the slope. And so you can see that at time of death, or at time of probe entry, I should say, our zombie was about 65 degrees C, and at every unit time that we moved out, remember, it was once every 10 seconds, it loses about 0.008 of a degree. Okay, so it's very slow right now, very slow rate of change for 10 seconds. Okay, and so we can use those as our parameters to create the equation that you saw we've already got. Okay, if I pull this down a little low, you can see that 65.4 is right here. That's the intercept, and the slope is about 7874, depending on the significant figures that you use. If I pull this out, well, I could change that, sorry, and get the different significant figures. Where's figure 1, sorry. And you can see that's the slope. So the entire equation is completely fixed. Okay, we know it completely by those two parameters in the beta matrix. Okay, that's beta. We can then come down and we can see y hat. Y hat is the predicted values of temperature, okay, for each value of time. So these are all the predicted values. Given our linear model, if I plug all the values of time into the linear model here, I will get these values, y hat. Remember, the y has that little caret over the top of it as a traditional symbol, so we call this the hat matrix, or the predicted matrix. This is y hat. In this case, it's just a vector because we only have one dependent variable. Okay, so we have beta, the parameters. We have y hat, the predicted values. Okay, we have r, which are the residuals. Okay, those are the differences between the predicted values and the actual values. Okay, you see half of them are negative and half of them are positive. Okay, so we have the residual values, and so we can do a residual analysis with stats.r. Okay, we have a bunch of other things that I use a lot, but you won't need to right now. The degrees of well, no, that's not what I wanted. Sorry. Stats. There we go. Sorry. We've also got the r squared. Okay, it's just like we got on the other model. That's our r squareds. It's about 97% of all the variation in temperature is predicted by time. So that's a very, very tight model, very little error of prediction. And then we come down here, there's two others that you'll want to know right now. There's the t statistic, okay, and this is the t-test of the slope. So if you get, there's a bunch of things here. You get our beta weights, right? These are beta weights, the intercept and the slope. This is the standard error of the intercept. This is the standard error of the slope. So if I go into that, I can get those are the denominators of the t-test, okay, for the intercept and for the slope, okay. I can get the t value itself, okay. That is the t value 2.19 times 10 to the 3, very large, right? 2000 is for beta 0, okay. So the intercept is significantly different from 0, right? 65 degrees Celsius, that's pretty significant from 0. And the slope has a t-stat of -46. So that's again, a huge magnitude of t in the negative direction. Now we want to say, is this significant? Is this a significant model? We can go back and we can take a look at the probability values, p-val, and you can see that the intercept has a probability of 9 times 10 to the negative 149. Okay, just infinitesimally small. It's highly unlikely that our intercept that we've modeled is due to random chance. It's due to a significant relationship. And then the slope, 1.75 times 10 to the negative 48, also, this is exceptionally small probability value. And so we can reject the null hypothesis that the slope is 0, that we have a horizontal line. We don't have a one-to-one function. And we can say, yes, we do have a one-to-one function. There is a significant relationship between temperature and time for a cooling zombie. And I think that's all the data. Let's get, I don't even know what I've got open now. I want to go to stats. Where's just stats? There it is. So there's, and so there are many other things that you can use in this, but right now that's all you really need to know for simple linear regression going into the midterm. All right. Now, how do we use some of this data? We need to do a residual plot. So what I can do is I can take the this R vector, right, stats.r, and I can scatter that on time. Okay, that's our independent variable, and then stats.r. Actually, let me save what we've already got so far. Let's get a new figure. Now we're going to do scatter. Time, comma, stats.r. And we can take a look at the scatter of the residual. And we look at it, we see it's pretty random. It's pretty equally distributed, about 0. There's no real pattern to the data in sense of for most of the data, in sense of quadratic pattern or something looks exponential. This looks pretty evenly distributed on both sides of 0. The big problem we have is this stuff at the beginning. Okay, remember when we took the data, when we first put the probes in the zombie, the probes had to heat up, and so we've got this weird cooling curve here that doesn't match the linear. Well, it's close to linear. It's actually just a very small rate of change, exponential. Okay, we got this part here that doesn't match the rest, so we would have to choose what to do. We can lop off this beginning and say it's heating up. That's actually not the cooling of the zombie, right? Claim that that's not real data. The only real data is this part right here, and then we could get an even better model by lopping off that data and running the regression again with a reduced data set. Okay, and we can also run a QQ plot, quantile plot, on the residuals. Okay. And this shows that we've got some issues. So even though the scatter plot of our residuals didn't show any real anomalies except for at the beginning, this shows that we've got some weird stuff going on in the middle. Okay, we've got two basic functions that both kind of differ from each other quite differently, probably each due to the different probes, different to the different rates of warming up versus cooling. Okay, so we may have to go in and fit an exponential model to this data. Okay, this is a bounded exponential, and we'll teach you how to do that in the next tutorial. But this tells us that this is the residuals, the residual values that are on the input sample do not match what we would predict if they were randomly and normally distributed. If they did, all of those blue crosses, all the data residual values would fall on this straight line. Okay, so the model is not randomly and normally distributed. There's something going on. So we can assume that a linear model is probably not the best model, even though it fits the data almost perfectly. It's not necessarily the correct model for the real relationship among the data. For the range of values in our problem, it's good enough. I mean, it's very close. However, if we try to extrapolate that out to all the way down to room temperature, we would have a real problem with the data because of that, because it actually gets asymptotically shallower, approaching the ambient temperature in the environment. Okay? It's not a linear model over the entire domain of the phenomena. All right, that is the everything that you need to know about regression. You put your data in, okay. Do a scatter plot, see if a linear model might be appropriate, okay. Run your linear regression. Do a residual plot. Do a QQ plot, and then if you need to, transform the data, run it again, and go through the process. All right, I am going to stop sharing, and you have a lovely day.